So today we will develop a technique that will help us understand the setting up of the time-dependent perturbation series in a more effective fashion. Okay, so before we begin, let us actually quickly go through what we did. Not the example, but the philosophy behind time-dependent perturbation theory. So you start with the assumption that you know everything about the unperturbed Hamiltonian, the H0, right? You know how to figure out the eigenstates and eigenenergies. And of course, since it is a Hermitian operator, you can expand any state as um, a linear combination of the eigenstates of H0, right? Now, H0 itself cannot cause transitions between the eigenstates of H0, right? So once you start off with some state N2, you always stay in that state N2 because H0 doesn't cause transitions between the states. All the time dependence is encoded in this exponential factor, e to the minus int over h bar. Now you turn on a perturbation, which is a time-dependent perturbation. And the way we solved it is as follows. We want to understand the effects of h tilde of t. So look, psi of t, when you start out with some vector, the time evolution of the vector now has two parts to it. The H0 also causes a time evolution, but the time evolution is actually quite simple and you know it already. It is e to the minus in0t over h bar. But h tilde of t also causes time evolution, which you do not know. We do not know in general how the state vector changes once you turn on the perturbing time-dependent Hamiltonian h tilde of t. So to codify the effects of h tilde of t, we wrote down the state vector as sum over n dn of t e to the minus ient over h bar over n0. So this guy, right? Oh, so just 1 minute. So this equation, okay, this is what I'm talking about. So this is fundamentally what I want to basically talk about. The time dependence of the H0 has been factored out in this equation. And this was a deliberate choice. We didn't have to do it, but we made this choice simply because we want to understand everything that we want to understand about the state vector we claim is now contained in the coefficients dn of t. And what is dn of t? dn of t is the time evolution of the state vector that is arising purely because of h tilde of t. Okay, so we developed a formalism which is very similar to the time-independent perturbation theory setup, wherein we try to develop a formula for dn of t without taking recourse to looking at h0 over and over again. In other words, what we did was to set up a formula for d in such a way that all the time dependence due to H0 is already factored out and all information about H0 is finally eliminated. And we only have an equation for D. And what is D? D is the time evolution due to the perturbing Hamiltonian. Okay. So when all is said and done, we got this boxed formula. And in this boxed formula, you see that there is a D dot on the left-hand side and a D on the right-hand side. And then the matrix element is simply the matrix element of the perturbation between the unperturbed states. So there is no H0 in this formula, right? So, and this is a formula that only tells you what is the rate of evolution of this D, okay, given a perturbing Hamiltonian H tilde. And the e to the I omega fn t is just the exponential factor. This is a remnant of the e to the I en0t over h bar. Now, one important point about this equation, as we discussed in the last couple of lectures, is that this cannot be simply treated as a solution because we want to find D, and D is there on the left-hand side and the right-hand side. And the right-hand side is there in a very non-trivial fashion. It is a sum over all D's, right? So we have to take recourse to what is called a perturbation technique to solve this equation. And the way we did this was basically solve it order by order. And to first order, we developed a formula for df of t, which is given here. Once my sharing comes back on, which is given here. Okay. So the development of this formula preceded by us wanting to concentrate on the perturbation and having factored out all the H0. So it turns out that there is a more powerful way in which one can do this. Of course, I can continue that procedure. I can simply do it order by order and solve it, but there is a more elegant way of looking at the entire picture, which is based on the same philosophy that we somehow want to freeze out the time evolution because of H0, and when we only want to keep track of the time evolution due to H tilde. Okay, so we will develop this elegant picture starting today. So what is it that we want to do? Before we start doing, let us actually basically tell you, let me actually tell you what it is that we are going to do in principle. It's actually quite simple. So let us say that you have some kind of a rotation. Okay, so you have some kind of a rotation u1 and you have some kind of a rotation u2. Okay, so this rotates by some angle alpha and this rotates by some angle beta. Okay, now of course you can act it on the Hilbert space and all your vectors get transformed and you can look at the transformed vectors and things. Okay, but suppose let us say that you only want to understand the properties of this guy. Okay, you really don't care about u2, let us say. Okay, this is an artificial example, but in principle, this is what we would be doing. Then what you can do is basically say that, look, since I don't want to keep track of u2 of beta and I'm only interested in u1 of alpha, I will basically transform to a new frame where all my new vectors are basically u2 dagger times psi. Okay. Now, if I transform to a new basis where all my vectors are u2 dagger beta times psi, then an operation like this gets transformed to u1 of alpha times u2 of beta, not acting on psi, but now u2 dagger beta acting on psi. Okay, this way, since this is a unitary operator, u dagger simply becomes 1 and I can only keep track of the u1 of alphas acting on the psi. Basically, my trick in trying to neglect u2 and only keep track of u1 is to do a basis transformation wherein all the effects of u2 beta are frozen out. This is exactly what I'm going to do, but I'm going to apply this to the perturbing and the unperturbed part of the Hamiltonian. So what is it that I'm going to do? So let me erase this part. And what I'm going to do goes by the name of interaction picture.
Hello, sir.
Yes.
Sir, here is one thing I don't understand. When you were saying that you wanted to understand u1, and that's why you modify the psi. But sir, if psi itself is changing, then sir, I mean, I don't understand why should we.
Yeah, that is a sort of a rough idea. Of course, the operators themselves will change, right? If I do a basis transformation.
Yes, sir.
States would change, the operators would change. I have to keep track of everything. I will keep track of everything, but that was simply the motive, what it is that we are going to do. I will do this a little more carefully and demonstrate explicitly that what we are going to do actually achieves our goal. What is our goal? So again, think of this in a classical mechanics way. For example, if this makes you uncomfortable, right? So let us say that there is a guy running along at 10 miles an hour, right? Now, basically what I'm saying is that I don't want to look at the guy running. I don't want to keep track of his velocity. So let me actually boost to a frame that is also running at exactly the same velocity as him. So in this frame, he is frozen, right? So the quantum mechanics statement is a little more complicated, but in principle, that is what we are doing. So we have a Hamiltonian. So our Hamiltonian H, excuse me, is H0 plus H tilde. Okay. Oh my gosh, this thing is really horrible today. Give me a second. Sorry about this. Okay, so my Hamiltonian is h0 and h tilde, and my state vectors time evolve. How do they time evolve? Well, that is the fundamental question, right? If I can figure out how the state vectors time evolves, then I know the answer to everything. I basically have to solve the Schrodinger equation. What is the Schrodinger equation? IH bar d dt of psi of t equals h0 plus h tilde of t psi of t. Okay. The premise of the problem is that in general, this differential equation might be difficult to solve. So, which is why I resort to approximation techniques. Okay. See, if h tilde was absent, I know exactly what the time dependence is, right? If h tilde is equal to 0, then I know psi of t is basically is some unitary operator that you know t0 times psi of t0. And in this case, I can solve for this unitary time evolution operator exactly. And I know that u of t comma t0 is e to the minus ih t minus t0 over h bar. Okay, in the case where h tilde is equal to 0. But if h tilde is not equal to 0, this is not the time evolution operator. I have to solve this differential equation. Okay. But my goal here is to somehow not keep track of this original u of t t0 that is arising because of h0, and I only want to keep track of the time evolution due to h tilde of t. So I'll have to do a basis transformation, and the way I will do the basis transformation I'll explain in just a second. And I'll have to ensure that the basis transformation I do, it's not really a basis transformation in that sense. It is actually if I'm thinking of this in terms of rotations, it is basically rotating my frame in such a fashion that I freeze out the time dependence due to the unperturbed Hamiltonian h0. Okay, that is what I'm doing in words. In formulas, it is actually slightly easier to follow. So what it is that we are going to do. So the picture that we are used to, so this way of looking at it, what we are doing is basically what is called the Schrodinger picture. So since I'll be talking about a new psi that is not a Schrodinger ket, I'll have to keep track of which is which. So I will denote all the Schrodinger kets by a subscript s. Because the Schrodinger equation in the Schrodinger picture will be written as IH bar. So Schrodinger picture IH bar d dt psi s of t equals, now I have to write h0 psi, so I'll put the 0 on top and reserve s for the Schrodinger subscript. So h0s here is the unperturbed Hamiltonian in the Schrodinger picture. Similarly, h tilde s of t times psi s of t. Okay, so this is the Schrodinger equation in the Schrodinger picture. We are also used to what is called the Heisenberg picture. In the Heisenberg picture, so this I can write the entire thing as h. Okay, where h is h0 plus h tilde. Now, you're also used to Heisenberg picture. What is the Heisenberg picture? In the Heisenberg picture, you freeze out the entire time dependence of the ket so that the ket is actually time independent, and you dump all the time dependence on the operators. But that is not quite what we are going to do. What we are going to do is somewhat in between the Schrodinger picture and the Heisenberg picture. In the Schrodinger picture, we say that the operators don't time evolve, but the state vectors do. The Heisenberg picture, we claim the state vectors don't time evolve, but the operators do. But what we are going to do now is what is called the interaction picture, where both these guys time evolve. This on the surface looks a little complicated. Why would we want to do that? But it achieves our goal of giving us an equation that only talks about the time evolution due to the h tilde part. Okay, so that is what we are after. So how do I set this up? So let me define this u. So again, the solution of the Schrodinger equation in the Schrodinger picture, I will denote by this. So the solution to the differential equation that I have just written down. Suppose if I can write this as u psi s of t is some propagator u t t0 psi s of t0. Okay, where u, again I'll put a s here, is the solution to the entire problem. Okay, it's a solution to this equation. Okay, but suppose if I don't look at the h tilde, suppose if I only want to look at the free part, then the solution to this equation you already know, and I will write it in this exact same language. Psi s of t in this case is us0 t t0 psi s of t0. Okay, so please understand the difference between the first line and the third line. In the first line, I'm writing down the time evolution of the Schrodinger ket with regard to the entire Hamiltonian. Okay. In the third line, it is just the time evolution of the Schrodinger ket with the h tilde switched off. So that is why there is a 0 in this propagator. This u we will call a propagator following Shankar's notation. Why is it called a propagator? Because it tells us, given a state vector at time t0, what does it propagate to at time t equal to some other value t. Okay. Now, in the unperturbed case, us0, you already know what the propagator is, right? It is e to the I capital H of t minus t0 over h bar. That is something you know. Okay, so it is easy for you to understand certain important properties of the propagator that will be true regardless of whether I talk about us0 or us. So the propagator is a unitary operator, which means u dagger u is always identity. Okay. Now it should also be obvious to you that if I take the system from, let us say, time t3 to t1 and t2 to t1, this is equivalent to taking the system from t3 to t1. Okay, so basically I'm piecing up my time evolution from t1 to t3 in 2 steps. I go from t1 to t2 and t2 to t3. Okay, now it's also true that u dagger of t0 is u of t0 t. Okay, this is also a property of the propagator. Now, it is not at all obvious from the first line because we don't know the form of that propagator, but it should be obvious from the us of 0. This is certainly true for us0, where us0 is e to the I capital H t minus t0. There, if I take the dagger, it is basically going to change by minus I to plus I. That is equivalent to changing t minus t0 to t0 minus t. Okay, so this these three properties of the propagator we will take seriously. So basically, we are claiming that if I can solve for the propagator us, so if you could solve for us, then we are done, right? Because that is fundamentally the issue. Given the state vector at time 0 seconds, what is the state vector at time 5 seconds? The propagator tells you that. So the question is, how do you figure it out? Given that h tilde is also time dependent, this might be a little complicated. So we will proceed carefully. So let us stick to the Schrodinger picture for now, and I can turn the Schrodinger equation into an equation for u. How do I do that? So remember that IH bar ddt of the Schrodinger ket is basically HS Schrodinger ket, and I also told you that we are working with the unsatz that psi s of t can be written as the propagator t t0 in the Schrodinger picture psi s of t0. Okay, so plug this into this equation. So I h bar d dt of us of t comma t0 psi s of t0 equals hs, and psi s is nothing but us of t comma t0 psi s of t0. Okay, I'm simply plugging in the form of the solution into the original equation, but I've not actually solved the problem because I don't know what us of t comma t0 is. That is my problem. I need to figure it out. Okay, so remember that psi s of t0 is not a time dependent function, right? It is just the state vector evaluated at the initial time t0. If you want, you can take t0 to be 0. So the ddt only acts on the u on the left hand side. So this tells us that IH bar d us dt times psi of s equals hs us psi s of t0. And since this has to be true for any ket psi s of t0, I can turn this into an operator equation and write as d us dt equals the Schrodinger, the Hamiltonian in the Schrodinger picture times the time evolution in the Schrodinger picture. Okay. So I will use this formula later. So I'll put a box around it. So again, don't lose track of our goal. Our goal is to not having to worry about H0 and write some things purely in terms of H tilde. Okay. So how do I move towards this goal? Well, if H tilde was 0, if H tilde equal to 0, then I should have IH bar, the above boxed equation, I should be able to write as d us 0 dt equals hs0 us0, right? In other words, equivalently, I can write psi s of t equals, us 0 t0 psi s of t0. So this is exactly my time evolution due to the unperturbed Hamiltonian. So now I am going to do a rotation in some sense such that I freeze out the time evolution because of the unperturbed Hamiltonian. So I'm going to define a new ket, okay, in this rotated basis, and I'm going to call this psi I of t. And psi I of t is going to be equal to us0 t0 dagger psi s of t0. Okay, this is my definition for the new ket. Okay, this I, the subscript I stands for interaction picture. So these are my kets in the interaction picture. So given my Schrodinger kets, my interaction picture kets are defined by this relation, where I take the time. So where I take the time, sorry, this is not psi of t0, it is psi of t. Okay. So if I have my Schrodinger ket at some time t, the corresponding interaction picture at that time t is basically us0 dagger times psi s of t. So how does this help us freeze out the time dependence of H0? Well, we'll actually see that in just a second, but roughly you can understand what's going on, right? If H tilde was 0, psi s of t evolves according to u times psi s of t0. So u dagger is simply 1. So psi interaction basically matches up with psi Schrodinger. In other words, at time t equal to t0, you can easily claim that psi interaction at time t equal to t0 is basically psi s of t0. Why? Because u of t0 comma t0 is nothing but 1. There is nothing to propagate, right? It's exactly same time. So the evolution operator is defined such that if you if you compute the evolution operator between time t0 to the same time t0, you should get one identity because nothing is evolving, nothing is changing. Right? That is the basic. That's another basic property of the time evolution operator. So I should probably write this down here. Okay. In other words, u of t1 comma t1 is just identity. Okay. Okay. So with this definition of my interaction picture kit, how do I set up the Schrodinger equation in this new picture? This is not the Heisenberg picture. Okay. Remember, in the Heisenberg picture, if we were doing the Heisenberg picture aside, Heisenberg picture would be freezing out the entire time dependence, not just the time dependence that is arising from the unperturbed Hamiltonian. So the excuse me, Heisenberg kit would be U dagger psi s of t. Okay. This means that psi h of t is not at all time dependent because psi s evolves according to us. So u dagger is just one. So psi h does not time evolve. This makes it basically frozen in time. Okay, so this is the essential difference between the Heisenberg picture and the Schrodinger picture. In the interaction picture, I am not freezing out the entire time dependence of the Schrodinger kit. I'm only freezing out the time dependence arising out of the H0 part. Okay, so I am still carrying with me some information about the time evolution due to Hi, but how I extract this information is basically the game. Are there any questions about this? Please tell me if there is any questions about the difference between the interaction picture and the Heisenberg picture. So please don't confuse the two. In the interaction picture, the state vectors are time dependent, unlike in the Heisenberg picture. Yes, question. Hello.
Sir, both seem same to me except for
no. The crucial difference is the zero on top here.
Zero. Yeah.
You see.
Okay.
In the interaction picture, I'm only freezing out the time dependence arising out of the unperturbed Hamiltonian. So this is basically, since I know U as 0, I know this is basically e to the IHS t minus t0 over h bar times psi s of t, right? But that is not the entire time dependence, right? Because h tilde also causes some time dependence. So I need to figure that out. So this state kit psi I of t is actually time dependent. I need to figure it out. Okay. So let's set up the equation in the interaction picture. Let's also understand how the operators evolve. So operators change. So as you know, in the Heisenberg picture, if this is my transformation, the operators change. AH is basically some U AS U dagger, right? So you will get something exactly similar in the interaction picture also. You will get U AS U dagger, but the U would be just US of 0. We'll figure this out exactly. So let us go back to the let us go back and set up the Schrodinger equation in the interaction picture. I don't understand how this new kit helps in freezing the time dependence. I haven't told you yet. Okay, so I will demonstrate in just 2 minutes that the Schrodinger equation you get for psi I of t has nothing to do with H0. I will explain. I'll demonstrate this in just 2 lines. Okay. So let us write down the Schrodinger equation for the interaction kit. So in other words, I need to understand what is IH bar ddt of psi I. Okay. What is this equal to? Well, psi I is defined in this fashion. So we can simply say, oh, this is just a Schrodinger equation. This is just H psi. But what is this H? I need to figure out what this H is, right? So is this the H0 or H tilde or both? I don't want H0. That is the entire point. So this is equal to IH bar ddt of US0 TT0 dagger psi s of t, right? This is my definition of the interaction picture kit. So this is equal to IH bar. let us do this carefully. D dt of US0, excuse me. So I will suppress this t comma t0 because I don't want to keep writing it. US0 dagger psi st plus US0 dagger d dt of psi s of t, right? So this is just chain rule. So, but I know exactly what the first part is and what the second part is because I know this equation, right? So, so IH bar, I know that IH bar d US0 dt equals HS0 US0, right? I know this equation. But I don't want du dt, I want d dt of u dagger. So just take the dagger on both sides. This is minus IH bar d US0 dagger dt equals US0 dagger HS0. Hamiltonian is a Hermitian operator, so H dagger is just H. So which tells me that d US0 dagger dt is 1 over minus IH bar, right? So that should be IH. So 1 over minus IH bar is just I over H bar. Okay, so this is I over H bar US0 dagger HS0. Okay, so this is, I know what this guy is. Okay. So I also know d dt of psi st because I know the Schrodinger equation. So I know that IH bar d dt of psi s of t is just Hs psi s of t. Where Hs is, this is equal to H0, sorry, H0s plus H tilde s psi s of t. Okay. So let me input both. So IH bar d dt of the interaction kit equals IH bar times the first guy is I over H bar US0 dagger HS0 acting on psi Schrodinger kit plus the second part is US0 dagger d dt of psi st is, excuse me, 1 over IH bar HS0 plus HS tilde acting on psi s of t. Is this clear? It is basically just a chain rule. I have not done anything great here. So the only thing that remains is just cleaning up this entire mess. So the first term is basically minus, because there is an I square, US0 dagger, HS0, psi s of t, excuse me. And the second guy is basically plus, and the 1 over IH bar here cancels with the IH bar out front. So I'll have US0 dagger times HS0 plus HS tilde acting on psi s of t. Okay. Stop me if anything is difficult to follow. I'm just basically solving this equation step by step. So this has two parts to it. H tilde of s, I don't know, so I'll just have to keep it as such. But I do know that Hs acting on psi s, what that means, right? So in fact, I don't have to solve it because that part cancels with this part. So this is minus US0 dagger HS0 psi s of t plus US0 dagger HS0 psi s of t plus US0 dagger H tilde s psi s t. Okay. So as you can clearly see, this term and this term simply cancel. So this is the reason why we are using this interaction picture kit, because all dependence on H0 simply cancel, and the time evolution of the interaction picture kit is purely decided by the H tilde operator. So we'll just clean this up in one final step, and then I will stop for the day. This is ddt of interaction picture kit equals. Now I still don't want to carry the Schrodinger kit along. I want to talk about the interaction kit. So since I know that the interaction kit is U dagger times the Schrodinger kit, the Schrodinger kit is basically U times the, interaction picture kit is U dagger times the Schrodinger kit. Schrodinger kit I can write as U times the interaction kit, right? Because U is a unitary operator. So I can write this as US0 dagger, HS tilde, US0 times the interaction kit. Okay. But as you can clearly see, if the kits transform this way, U dagger psi, the operators obviously transform this way, U dagger HU. So this combination U dagger HS US0 is basically the interaction, the perturbation Hamiltonian written in the interaction picture. So this part is nothing but Hi of T. It is the perturbation part of the Hamiltonian written in the interaction picture. So all said and done, this equation simplifies to something which is exactly what we want. It tells us that the time evolution of the interaction picture kit is decided exactly by the perturbation part of the Hamiltonian in the interaction picture times the interaction picture kit. So this is the Schrodinger equation for the interaction picture kit. Okay, and as you can clearly see, this has no information about H0. All the H0 part has cancelled off and dropped off. So if I can solve this equation, basically I know exactly what my time evolution is, but of course that is easier said than done. So we will continue with this tomorrow. We will turn this Schrodinger equation into a perturbation series and help connect you with the formula that we originally derived. Okay, so we'll stop here for today, and then we will continue in the next lecture where I will turn this into a perturbation series, but I will work in the interaction picture.